We're going to talk today about slot and pole selection for permanent magnet motors. Now, there was a famous British professor from Berlin by the name of Lucius Garrick. Very interesting guy. He was born in the last century, and he was married in the 20s, and he must have married a very hard woman, because when he got married, she insisted that she not take his name, but they use their names with a hyphen in between. Lucius Garrick. One is his family name and one is her family name. Very unusual for Germany and Berlin at that time. He was a famous machines professor, and he published a book on the balanced and unbalanced winding combinations for induction and synchronous machines. This is a famous textbook. It's the most famous in the English language now, because in 1950 he immigrated before that to the United States before the Second World War, and he republished this book in English. And it's a very famous text. There's a lot of patents been issued by the U.S. government and other countries around the world on slot and pole combinations, which is a tragedy, because the formulas and the principles set forth in this book, published years ago in Germany in 1950, United States, really negates all of those patents on slot and pole combinations, because they're all covered in this book. And there's beautiful diagrams of them. And I got exposed to this back 40-some years ago on the Apollo program. One of the first brushless motors ever that went into production, was ever used in the world, was on the Apollo program. And I actually was working under a student of Lucius Garrick at Clifton Precision, which is now part of Moog in the United States. And we developed this little actuator for the space program, and we made it a 12-slot motor with 4 poles. And this motor had a terrible cogging problem, and we couldn't pass the cogging spec, so we changed it to 15 slots and 4 poles. And of course, that disrupted the alignment of the edges of the magnets to the slot openings, and this reduced the cogging, and we met the spec. But I start with that because of the 12-4 motor, as we'll call it. And I'll call these motors by the description of the number of slots first and the poles second, the 12-pole, 12-4. That became very popular, and believe it or not, it seems like everybody made 12-4 motors, brushless motors. They were called brushless then. The inverter guys don't call them brushless anymore. They call them PMAC synchronous motors now, because when they were brush-type DC motors, the speed was controlled by voltage. But now that we use modern induction motor energizing techniques, the speed's controlled by frequency. So they're called PMAC synchronous motors. But the machine's still the same. So the same pole and slot and pole combinations apply. So we're going to study some of those and how these have transitioned over the time. It seems like the first 12-4s, everybody that got into brushless motors, they copied those combinations. And then when the disk drive industry started, back, when was that? About 1970 or something like that. There was a German, is anyone here from Pabst? The German company Pabst, they're in the Schwarzwald in the Black Forest. They developed brushless motors for these muffin fans, these little cooling fans for electronics. And in around 1970, IBM was the god of computers in those days. They passed a law. IBM, that particular law that they passed, said that thou shalt not use an AC machine inside of a computer. Because in Europe you have 50 hertz, in the United States we have 60 hertz. So if they used induction motors or synchronous motors inside the peripherals of a computer, they would have to change belts or pulleys or something to get the speeds to come out because of the 50 and 60 hertz. Plus they had noise problems with AC inside of a computer. So they passed a law that everything will be DC. And sure enough, that meant that for all computer peripherals, you either had to use a step motor or a brushless motor. And that's really what launched brushless motors to make them the commodities they are today, was the computer peripheral industry. And so Pabst in Germany developed the first disk drive motors that were used in the world. And these were, and they patented this, half a slot per pole per phase. You motor engineers will use that term a lot. Half a slot per pole per phase, and that comes out to 6 stator slots and 4 rotor poles. And that's a very simple, low-cost machine to make because the coils are wrapped around an individual tooth, so the end turns are very short, which package very nicely in a disk drive, and you could automatically wind them with these needle winders. So that was very popular, but they patented this, but then they abandoned the patent, reapplied, abandoned, reapplied. They applied for this patent on the half a slot per pole per phase design in let me see, it was 1981, I believe. And then it was abandoned. It was finally issued in 1998. Can you believe that? That patent was issued in 1998. By then, there were hundreds of companies all over the world that were already making big quantities of half a slot per pole per phase motors. And so they started to sue them. The Pabst family sued them. They started in Japan. And the Japanese don't like to make lawyers rich, so they didn't litigate. They agreed on a license arrangement. So you had 6 companies, including Panasonic, Hitachi, and Japan Servo, that got licenses with Pabst to make these half a slot per pole motors for all these quantities. And so then they started suing the American companies, and they had these historical events of all the companies that didn't go to court, so they lost all the cases in America, blah, blah, blah. But that patent should have never been granted in the first place because there's a book published in England by Professor Croft, C-R-O-F-T. And in 1924, he showed this in one of his books, beautiful ink drawings that show it wasn't a 6.4, it was a 9.6, which is still half a slot per pole per phase. So that patent should have never been issued because of prior art, but that's beside the point. So these are some of the things that go on with these slot and pole combinations. To get around those patents, many companies came out with a 12-slot 10-pole. Have any of you seen a 12-slot 10-pole? Now that's a very nice motor because it's got more sinusoidal shape of the back EMF than the 6.4 does without skewing or shaping the magnets. And it's a very nice motor. They developed that to get around the old Pabst patent. But 2 companies patented that as well. But that patent's not enforceable because I published that in my 1990 book on brushless motor design. So that one isn't enforceable. You don't have to worry about doing the 1210. But the U.S. Patent Office didn't know about that book, so they issued the patent, but it's not enforceable anyway. So the 1210 became popular, and then it seems like people play follow the leader in this industry. I don't know what it is. Sometimes they don't pick slot and pole combinations that are based on sound theory or requirements of the application. They seem to do a lot of follow the leader, thinking that the originator of it spent all the research money so they can save that money. Let's use the example, the Toyota Prius. The Toyota Prius came out in when? 2003 in Japan, 2004 in the rest of the world, and they used a 48-slot stator and an 8-pole rotor. And they don't even have 48 coils for those 48 slots. They only have 24 coils. So they only have 1 coil side in each slot. That's called a single layer winding. And the reason they did that is because that's a better thermal situation. If you take all the turns that you need and put some steel in between half of them, the steel will suck some of the heat out to the liquid cooling. So that's why you use a single layer winding, because it's easier thermally to extract the ohmic loss heat production from the windings. But if you have a high-speed machine, that single layer winding is going to give you proximity effect ohmic losses or at high speed. So there's lots of issues to consider when you pick these number of slots and poles. So everybody else everyone that copied the Toyota Prius, like Ford, like Nissan, like Honda, they all use the same thing, 8-pole, 48 slots, until General Motors decided to come out with an electric car, a hybrid car. So their motor was designed by Ramey in Anderson, Indiana, the company that used to make, or still makes, starters for cars. And they were used to what's known as hairpin windings, solid, heavy conductor that you form like a lady's hairpin, and you insert those in the slots and make the connections at the other end. But that motor is a very strange design. It is 10 poles and 60 slots, 10 poles, 60 slots, and it has 2 sets of coils in it. It has 2 coils with 1 turn, and another coil with 2 turns. So you wind up with 4 conductors in each slot, or 90 coils in 60 slots. It's a very strange configuration. Here at the show, I don't remember the name of the company, there's a company that's producing a small version of those hairpin wound stator coils. Very, very interesting. But that's a 60-10. Now, more recently, BMW has come out with a couple of electric vehicles. One is called the i3. It's a strange-looking car, but it's a beautiful piece of engineering. It has a complete carbon fiber body, and the motor in it, the electric motor in it, is a 12-pole motor with 72 slots. Now that's a very, very interesting motor. It has some extra saliency. I assume everyone knows what saliency is. This is a permanent magnet machine with the magnets on the interior, and it has some salient poles between the magnets, just like the Prius motor did. But in the case of BMW, they added some flux barriers, some slots, radial slots in the salient poles to increase the inductance ratio between the D-axis and the Q-axis, so they can get more reluctance torque out of it. So it's a real hybrid. It's a synchronous reluctance and a permanent magnet machine all in one. And what's interesting about these motors is the speeds they run at. These motors run at the Prius motor, the latest one, 2013, top speed is 13,300 RPM at 8 poles. That's pretty high frequency. The General Motors volt motor, that runs about the same speed, 12,000 RPM at 10 poles, and the i3 motor is about the same, 15,000 RPM at 12 poles. That's really high frequency. So they're not using broadband technology yet. These transistors that have very low on-state resistance or losses, I think some of them are using what's known as multi-level inverters, which reduces the losses in the machine. So there's all kinds of reasons why they pick these things. Here's a picture of some cross sections of some PM machines here. The 2 on the right are outside rotor machines. Now you might use a design like that in the wheel of a car or a truck or an earth mover or a farm tractor or something like that where the speed is low. You know, if a car is going 60 miles an hour, I don't know what that is in kilometers per hour. What is that? 80 kilometers per hour? Is that 50 miles an hour? Something like that. If you're going 60 miles an hour and your wheel is 2/3 of a meter in diameter, then that means the wheel's going 600 RPM. So that's pretty slow speed, and you might use an outside rotor motor like that with a lot of poles, so that you'd have a stator on the inside. And in that case, because you're in a wheel, you don't have a lot of axial space, so you could not use what's known as an integral slot winding. You'd have to use a fractional slot winding where the coils are wrapped around an individual tooth, so you have very short end turns. That's critical. That does 2 things. It keeps the motor width skinny, narrow, and it also makes it easy to automatic wind, because you can automatic wind a machine like that quite easily. Also, the end turns are losses. They're ohmic losses. So long end turns are ohmic losses. So this machine has very short end turns, just like the disk drive motor was like that. A lot of those were outside rotor, just like this. Okay, the top two here, these are what's known as SPMs. We call those in English surface mounted magnets. You can shape those magnets a lot of different ways. They can be bread loaf, they can be arcs. Sometimes if you have a stamped rotor core, you can stamp little dovetail angles in the side of the stamping and slide the magnets in from the edge so that they're retained, so they don't fly off at speed. If your speed is very high, with these surface magnets, you have to put a retainment sleeve around them. You have to wind some kind of material like Kevlar, carbon fiber, or even fiberglass. Then there's also the possibility to use ring magnets on these machines. And the shape of the magnet affects the cogging, and it also affects the shape of the back EMF, which is critical with how you're going to drive the motor. In the case of the ring magnet, the nice thing about a ring magnet is that when you magnetize it, you can build your magnetizing fixture to skew the poles, which increases the, it decreases the harmonics in the back EMF, and it makes it nice and sinusoidal, and it reduces cogging. So a lot of people will use those kind of magnets. MagnaQuench is a company that was started by General Motors. They're one of the developers of neodymium boron magnets. They've moved a few years ago to Singapore. And in Singapore, they decided not to make magnets, but just make powder. So they make the powder for all the people in the world that mold magnets, injection molded magnets. And they developed a process and a material for what's known as a hot press magnet. Years ago, if you wanted to make a sintered, thin-walled ring magnet, which is very desirable for production. You can magnetize it on skew. You can just slip it over a rotor. It's very nice for production. People like ring magnets. But the sintered ones, you'd have to make 5 or 6 of them to get one, because the other ones would crack when they come out of the sintering furnace. So that didn't work. Well, MagnaQuench developed a hot press process and powder that they can hot press ring magnets, and they don't crack. They get very high yield, and they have grades with very high remnants, or 40 megagauss Oersted energy product. Very high, just like the sintered magnet. So that's an interesting magnet to use. And these can also be used in Haulback magnets. Haulback magnets are magnets that don't need back iron, because you magnetize through the magnet itself. There's 2 ways to make them. I'm not going to go into that now, but this new hot press material that magnet companies make using MagnaQuench powder can be perfect Haulback magnetizations within the thickness of the ring, like that, so that there's no back iron required. So, but you have to pick, if you're going to use those kind of magnets, you have to pick the right number of slots to go with them. Now here's a chart that I developed years ago, back in 1990. I think the first time this was ever published anywhere in the world is a list of the balanced winding possibilities for slot and pole combinations. We made one of these charts for 2-phase motors, 3-phase motors, 4 and 5, but most motors are 3-phase, so I'm only showing you the 3-phase. And so these are the where you have the poles across the top, which obviously have to be divisible by 2, and you have the number of slots on the vertical, which has to be divisible by 3, because it's a 3-phase motor. So you have to have the same number of coils in each phase to have a balanced winding, and they're electrically 120 electrical degrees apart. So where you have X's is where you can have combinations. It's a very useful chart for motor designers to get started and look what their choices are. And you'll notice the 6-pole motor. There's very few slot combinations that will work with a 6-pole motor. It's unfortunate, because 6-pole is a nice number. 8-pole, all slot combinations are possible with an 8-pole motor. You'll notice the 12 slot, that's the 4th one down on the left, and the 10 pole motor. You might say, how in the world can you get 10 poles out of 12 slots? because 10 doesn't divide by 3. But if you think in terms of consequent poles, then you can wind up with good flux linkage with the phases from the 12 slots, even though you only have 10 poles. There are about 6 or 7 different winding combinations that you can do with a 12-slot, 10-pole motor. And you can find software. There's one software package that Infolitica makes called MotorSolve. And when you load up their winding editor, they give you all the possible balanced slot combinations based on this chart for any number of poles and slots you pick. And it lists all the winding layouts in descending order of the winding factor. Now, what is winding factor? Winding factor is when you have perfect flux linkage between the conductors in the stator and the poles in the rotor. Let me give you an example. If you have, let's go back to 4 poles and 12 slots, or 12 slots and 4 poles. So a unity winding factor, or perfect flux linkage, is when the coils are wrapped around 4 poles divided into 12 slots, goes even, 3. So you wind the coils around 3 teeth, and now the flux linkage is perfect as it can get because the coil is centered on the center of the pole, all right? Sometimes they'll short pitch a 12-slot machine. They'll short pitch any machine to get rid of harmonics or reduce end turn height. So if you wind that same 12-4 motor around 2 teeth instead of 3 teeth, your winding factor is reduced by a significant amount. I don't remember what it is. It might be 66%. What does that mean? That means that you're going to have to add turns to make up for the loss in flux linkage. So when you add turns, that takes up winding space. You might have to use a smaller wire, and that'll increase your ohmic losses. But sometimes it's worth it to short pitch a winding, particularly if you have lots of slots. Then short pitching one tooth doesn't affect the addition of. Doesn't mean you have to increase the number of turns that much. Maybe only 1 turn. If it's high voltage, that's insignificant. So anyhow, this is a very useful chart. Torquers, DC torquers that require very low cogging and very smooth rotation. You'll even have more rotor poles than you have stator slots. Those are called very low RPM torquers. There's a number of people making those around the world. Inland makes them in the United States, and there's a Swiss company that I know of that's a big manufacturer of those. And the coils are wound around an individual tooth again. Now let's talk about the number of poles. If you're doing an induction motor and the torque is under 1,000 Newton meters, you're stuck with a 4-pole machine. You just can't justify a higher pole number if you're going to put an inverter on it, because the leakage reactance goes up as you increase the number of poles in an induction motor under certain sizes, under 1,000 Newton meters. So your inverter has to be too big. It costs more. If you'll notice the electric vehicles in the world, only one of them in production uses an induction motor, and that's Tesla. Why they use it, I'm not sure. I think, is anyone from Tesla here? I know there's someone gave a paper on Tesla, but I think the reason they use an induction motor is because he named the company Tesla, and Tesla invented the induction motor. I think it's a marketing thing, but I don't know that for sure. Maybe I'll have a chance to ask him, but every other company in the world that makes electric cars or hybrid cars uses permanent magnet machines. Why? Because that's the highest torque density we know about. Remember I said there's 2 magnetic fields in those, did I say that? The induction motor and the PM motor have 2 magnetic fields, one in the stator, one in the rotor. Reluctance motors only have 1 magnetic field in the stator, and the rotor is part of that circuit. But in induction and permanent magnet, there's 2 fields, one in the rotor and one in the stator. Well, the induction motor has got to apply power to the rotor, to that field. So you have ohmic losses, so it heats up. How do you cool it? you see? So an induction machine can never be as efficient as a PM machine if everything else is equal, because the permanent magnet field is there once you magnetize it. We've been told since we were children, nothing in life is free. Well, there is one thing that's almost free, and that's the force you get from a permanent magnet. Sure, you got to buy the magnet. Sure, you have to magnetize it, but once it's magnetized, you have that force field forever. So that's very elegant. That's the most elegant thing about a PM machine. So to prove this point that induction motors have to be 4-pole under 1,000 Newton meters, this says 1,000 foot-pounds. That's what's 1,000 foot-pounds, about 1,300 Newton meters, about the same. Reliance Electric, which is now owned by ABB, their engineers did a study some years ago when inverters started to become popular to drive induction machines on the factory floor. And they discovered, they studied this number of poles. And that's when they found that if you look at output number of poles, and these are difference between, I don't know what TEBC means. I'm not sure. What does that mean? Oh yeah, fan-cooled or not fan-cooled. So there's some differences in how it's framed and cooled, okay? But basically, under 1,000 foot-pounds or Newton meters or something like that, you're stuck with 4 poles. You might get away, you get close to 6 if your torque's a little higher. And the reason is because as the motor puts out more torque, the span between the poles is bigger. So less of a percentage of flux leakage from pole to pole. That's why in large machines you can have higher pole counts, but they tend to be low speed. In general, high-speed motors have low number of poles, and low-speed motor have a high number of poles, don't they? And what's important about the number of poles is that every time you double the number of poles, the yoke of the stator punching is cut in half. Now, a 2-pole motor has got a real thick back iron. You go to 4 poles, that's cut in half. And that reduces the weight of the motor 30–40% because there's so much mass in that yoke in the outside of the machine. What can you do with that when you increase the number of poles? Well, you can either leave the stator the same diameter, make the rotor bigger because the yoke is thinner, and you can make the motor a little shorter. Or what you can do is you can leave the rotor the same diameter and reduce the OD of the stator, whatever's convenient to fit in your application. But the point is that all of the hybrid cars in the world use 8 or more poles, whereas the Tesla uses 4 poles. So their motor's bigger and heavier, I guess. In induction machines, you have the same number of poles in the rotor as you have the stator. In PM machines, you don't need to have the same number of poles that you have in the stator because like this 1210 motor. Do you know you can wind 2 coils per phase? You can have 6 coils in that motor. It runs just as good. That's one of the winding combinations. Or you can have 4 coils per phase. 4 coils per phase. You have a pair here and a pair here, 180 degrees apart. Or 1 and 1. So you need software to really look at these things and get your arms around it. But here's some cross-sections of some of these goofy motors, the interior, the IPM motor, and the surface mount on them. Now, the top one there, the center one, is very interesting. The Toyota Prius doesn't have a very good sine wave. It has a little droop in the middle. So when Toyota did the Lexus, they did it like this. They put that little magnet, they thinned up the magnets, increased the V angle, and put this little magnet there, which makes the sine wave much better, okay? And the other thing that they do, this doesn't have much to do with slots and poles, but you see this distance between the magnets, that's called the salient poles. That's where the reluctance torque comes from. And they've done, everybody designs these motors spends a lot of time, a lot of work adjusting the angle and the width of that salient pole in between the magnets. It's tedious. It takes a lot of trial and error because there's no way you can sit down and there might be a way to calculate it, but it would be so complicated to come up with a whole set of variables and have a computer solve for that it's better just to model it with some fast solving field solver or something like that. So that's critical. Here's the slide that shows the shape of the machine. Each one of these has the same rotor diameter, and you see how the yoke changes thickness and how much smaller the motor becomes as you increase the number of poles. That's all because of reduction in half. Every time you double the poles, you half the yoke thickness. Now, another thing about these machines, if there's high speed involved, like an interesting little side note here is when the engineers at Toyota designed the Prius, they designed it as an IPM for magnet retention. That was their reasoning behind that. That's what justified that, because a car goes over, in the United States, we got bad roads. We got chuck holes inside of chuck holes. So if you're bang, 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 that's rough on the motor, and the magnets can come loose if they're mounted on the surface, and they would have to band those with something, with some yarn or some stainless steel. So they decided, why throw the hole away in the stator punching? Let's make that stator punching with some slots in it. And the very first Prius didn't have the magnets in a V. It just had a flat, thin, simple, cheap magnet with no grinding inserted in slots in the inside, and the leakage flux was acceptable for those little parts of the lamination that held the magnets intact, so they didn't yield the laminations. They didn't move, because if they moved, they'd go out of balance. But that first motor had a top speed of 5,600 RPM. Now they're up to 13,000 RPM, so it's a lot different now. So those little sections that hold that thing together in the corners of the magnets are thicker now than they used to be. But it didn't take them long to figure out that there's another advantage to the IPM, and that's the saliency ability of those little sections of steel between the magnets. So they played around with that, optimized that a lot. And if they didn't put it, if they made that magnet narrower to increase the saliency, they get less flux from the magnets. So that's why they made it in two pieces and put it on a V. I don't know if that was done before Prius or not. I suppose it was, but they're the ones that made it popular, and everybody copied them. So the higher speed machines, if they're surface magnets, you have to retain them. If it's an IPM, you have to use part of the lam to retain them. But and that retention method is always in the air gap. If you make it an IPM, then you have flux leakage in those little sections. You lose flux from that. It saturates, of course. But if you put the magnets on the surface, the air gap has to be bigger to make space for the retention system. So if you look at an axial flux machine like this one, you can put a big, thick, here's the magnet structure that's spinning, and there's centrifugal forces on that. The diameter tends to be big, so the centrifugal forces are pretty high. So all you do is put a thick piece of alloy steel on the OD to retain it. It works nice, and the key is it's not in the air gap. It's not in the air gap, so you can still have small air gaps with this machine, and you don't get any eddy currents in that thick sleeve that holds the thing together. There's basically two types of windings: integral slot windings and fractional slot windings. I guess I've already kind of alluded to that. The fractional, an integral slot winding is one where the number of poles divides evenly into the number of slots. A fractional slot winding is one where they don't. And you can divide, if you look at some of the publications I've done and the books I've written, you'll see classifications of these fractional slot windings: 2 1/4 to 1, half a slot to 1, 1 1/2 slot to 1, 3 to 1, 6 to 1, 4 1/2 slot to 1. So there's families of these fractional slot windings. And the shape of the back EMF is the same for any motor in that family, okay? And but the advantage of some fractional slot windings is that the coil is round on an individual tooth like I showed you, like these. You see at the bottom here, you have these integral slot windings. These are all fractional slot windings, and you can automatic wind these. The lower left is an inner stator and an outrunner. They call that an outrunner. So that's very easy to wind. That's wound like an armature of a DC motor. So you can wind all three phases at once. You can have three flyers 120 degrees apart, wind three phases at once, index that, have the finish of one lead connecting to the start of the next coil. Very cheap, low cost. You'll see winding machines all over this place that do that. Then the other one, if the stator's on the outside, the picture on the left, that's a needle winder. That's a little needle where the wire goes up through the hole in the needle and winds it like that. But other people have even changed that, and they stamp the lamination with individual teeth and stack them and put those on a high-speed winder and wind the coils right over the OD of the tooth itself, and you can taper wind that. You can wind, when you needle wind, you can't fill all the slots because you need space for the needle. But if you break that stator up into individual teeth and wind on that, you can taper wind and fill up more of the slots. You'll even see some here where the whole stator is hinged, the stamping is hinged, and so the stator teeth are laid out straight. I got pictures of that. I don't know if they're in here or not. Probably didn't have enough space to put them in here. But you just have a strip of lambs with teeth on it like that, and a winder winds around those automatic, and then you wrap this up and shrink it into a housing. That's very high volume, and you can taper wind that. Now, at the top here, well, you see on the left, that's another one of those needle windings, but that's heavy wire, so those were probably not wound in place. They might have been inserted. I'm not sure. The distributor winding, the center one's a very interesting stator. That's used in alternators for cars. And I don't know if you've seen how those are made. It's a fabulous production. The winding, or the stator lamination machine was developed and patented by General Electric back in the 30s, many, many years ago when this alternator first came out, because it's a fairly big stator and it's got a big hole in the center, so there's a lot of wasted steel. So for high volume for cars, they didn't want to do that. So it's they take a strip of steel and they have roller dies that punch the teeth out, and then they wrap this up like a slinky. You remember a slinky toy that you lay this on the stair step and it goes down the steps. It's wound on edge. Well, that's the way that those stators are made. They're still made that way to this day, but the patents, of course, are all gone, so they're made all over the world that way. And then the way the coils are wound and put in there is amazing too. But it's a tremendous piece of production engineering. But a lot of guys now, they'll go to the junkyard and buy these alternators and take the claw pole rotor out, and they'll put a permanent magnet rotor and make a little wind turbine for their house. A lot of people are doing that. But this stator on the right, that is a very interesting stator. That's the one that's developed by Ramey for the Chevy Volt. You see that square wire there? That's really an incredible design. There's four conductors per slot. And you want to have as many of the conductors linked with the rotor magnets as possible. We talked about that. This is kind of complicated. What this does, it talks about the winding pitch. You see the example, the 360 degrees divided by 4 poles is 90 degrees. So so I talked about that, about the slot pitch over the magnet pitch. That's what all this is about. You can study this. Let's see. The winding, I guess the winding, the 12-4 That's what I said before. The 12 pole has 100% or a unity winding factor, but if you short pitch it over 2 teeth, it drops to 66.6%. So you got to add like a quarter more turns to that motor, as I said before. This is too complicated to, you got to read this, I guess. But all these families of motors, these are all available, by the way. I'm running out of time anyway. Let me show you this one. This is very interesting. This is the last one I'm going to show you because I'm out of time. The 2010 Toyota Prius, they developed a new generator stator, and the rotor is different too. If you study these coils, every other coil is wound with parallel sides. The ones in between are wound with tapered sides. Okay? So this stator punching has no tips on the teeth. These are just poles from the punching that look like the poles of a switch reluctance motor. So what they do is their robots assemble the tapered coils first. Every other coil is a tapered coil. And that allows them to insert the ones with parallel sides because they go straight in directly over too. So this gives them very high slot fill in that generator. They patented that, but I suppose you could use it for another application. They won't bother you if you use it for a car generator. They'll probably sue you, but otherwise you can use that. They get very high slot fill for that, and those coils are wound on a bobbin, which is molded, so those bobbins go on a very high-speed winding machine that layer winds that wire, and then they're all automatically inserted there, and they have terminals in the bottom that the start and finish is attached to these little mini magnet terminals so that they can make a quick connection to all these coils for the generator output. And for the 2010, they changed the rotor. They have the magnets in a V on the rotor as that as well, but there's no saliency between them. They just wanted to get more flux. So instead of having a magnet like that, they put it on a V. They make the total magnet area more, and they get more flux. They don't need so many turns for the voltage they want. So, and I've given you a list of references of all the other papers and articles that cover all this stuff. And if you need a good book on how to design these machines, there's a book that Professor Miller and I wrote. So, thank you very much for attending. I hope you got something out of it. You have any questions?